In this video, we are going to understand what concave lenses are, what convex lenses are, and how to work with them. What are the important formulas? First of all, we will identify, how to figure out whether it is a concave lens or it is a convex lens. It is a simple thing, but sometimes it gets confused. I used to get confused because we already learned about the convex and concave mirrors, and now we are coming into the lenses. So there should be some common logic we should bind that, and so that we understand. If we understand the mirrors, convex and concave, we are also able to understand lenses, what are convex and concave. So there is something common in that. So let's say if you know what is a concave mirror. So remember this word, a cave, right? So a cave kind of a thing. This is a rough surface. It's a mirror. So after the cave, what you are seeing, reflecting surface. So this is a reflecting surface. When we were learning about reflection rules, we studied this. And now because we are learning concave lens, so there will be cave again. There will be cave. But now because we are studying about the refraction, so there will be no rough surface, and mostly we'll get shape like this, both side symmetrical. And after the cave, you are getting refracting surface. So both sides there are caves, but in case of mirrors it was a reflecting surface, and in case of lenses it is a refracting surface. So that is the commonality between these terms, mirror and lenses. If they are concave, what we should accept, we should look for the cave. It will be caved in. Okay, so let's go next. So what about convex mirrors and convex lenses? So in convex, whenever you hear the word convex, expect a bulging thing, like a bulge. So like in convex mirror, there will be a bulge. Rough surface will be this side, and the bulging reflecting surface will be there. Reflecting surface. So this kind of mirror, which you can find out in parking spaces. So convex mirrors are used in that. So convex mirror is this shape and identify with this bulge protruding outwards, like coming out. So you guessed it now. What will happen in the lenses? Bulging out. But one difference is that both ways, because it's a refracting surface, so it has other side also refracting. In the mirror, that only one side we're working with, but in lenses, whether it is a concave lens or convex lens, we have two sides, right? And it's bulging from this side. And what are these bulges? They are nothing but refracting surface. So look for this. So you will find out whether it is a convex mirror or convex lens. Okay, let's go forward now and understand a convex lens, bulging refracting surfaces, and we will work with that, and also we will note down and understand some technicalities, some technical words as we move. So for example, if I have a bulging refracting surface here, so this is my convex lens bulge. So if you see geometrically, what is its center? This point, right? So this point will be called optical center. We denote it by O, right? So this is our first technical term, that is optical center. If you see what is optical center, it is a point which is geometrical center of the lens. So geometrically, if you see where is the center, of course here it is, right? Geometrically we can find where the center is. So that point is called optical center. And for our reference, whenever we are using lenses, we draw an imaginary line which passes through the optical center and the centers of these curvature. So for example, if this is a circular, right, this is a circular arc, if you see, it will have some center. Let's say this is its center. Okay, so if you see what this line is, this principal axis is passing through, first thing is optical center, and then the point center of these curvatures. Why I'm saying curvatures? Because this side will be one center, and if they are symmetric, same distance here, it will be, it should be symmetrical somewhere here if they are symmetrical. So these points and this point, if line is, if we draw a line, we call it principal axis. So this is another technical term. Okay, so optical center, then there is a line crossing through optical center and the centers of curvatures, these arcs which are making, which the lenses curvatures which are have center. So through that, if line goes, that we will call as principal axis. Okay, now let's go further. Object, we will generally put object like this, arrow. You can use anything, but generally in our textbook we use an arrow. There is some advantages which when we will be moving forward, you'll understand why we are using arrow. So this distance will be d of O, or distance from optical center to where you have kept the object. So that will be called object distance, or DO. Now where is the image is formed? Let's see. Two lines here, two light rays, like one light is going like this. Okay, so it will converge because the shape of our lens is like that. So it blend downwards, and see, here's a point which is where it is meeting on principal axis. This is called focal point. Okay, we denote it by capital F. This is focal point, and distance from the optical center is denoted by small f, which is called focal length. Okay, the distance from the optical center to the focal point. Okay, so can we define focal point? Where the parallel rays converge. So they will all converge on this point only. So focal length is where focus is there or where parallel rays converge, and in case of concave it will diverge, appear to diverge from that point. We can also find where the image is with the diagram. First thing is we can draw a parallel line. Okay, so we know it will go to the focus. Okay, focal point, it will pass through that, so it will go like this. And because we know that the line is going through the focus, okay, if we do the logic reversed, like if a line is going through the focus, if this is symmetrical, let's say this is the focus this side, if a light ray goes here, okay, if it goes through focus, if a light ray is going through focus, it's passing through focus, it will go parallel, so we will get the reverse of it, right? So we can get a reverse of it, so it will become parallel. And now if you can extend this line, it will cutting on this point, so the top point image of this arrow's head will be formed here. So if the head is here, where are the feet? Feet will be here, right? So maybe it is getting formed here. It's a rough image, it's not correct, but just letting you know what does that mean, how the image will be formed, and graphically how we get to know that. And now see, if this image, my object was placed here, but you will say, oh, but my image is inverted. So this is a word upside down, right? The image is upside down. So this is inverted image. Okay. If the image comes straight like this, we will say it is erect. Image is erect. So there's another fancy word for that because they're really coming into the questions. Now, if you know all these points, so there are certain formulas which we need to look into when we are solving a lens problem. Okay. So one is the relation between focal length. Remember, small letter f. Okay. Di, distance of image, and do. Okay, so there is one relation between these three, and that is just a reciprocal of that. Very easy. Reciprocal of focal length will be equal to reciprocal of image distance to reciprocal of object distance. So this is our first formula, and no need to remember it again. Same formula we have used for mirrors. So that is why it is very necessary to whatever we have learned in the mirrors case. We try to find what are the commonality here so that things becomes easy for us. Okay, so if the relation between f, di, and do was this, can you remember what is the formula for magnification? Okay. So magnification, it was hi divided by ho, the height of the image divided by height of object. Okay, in terms of di and do also we can write, but we just need to use the negative sign. Instead of hi by ho, now it is di by do, and with the negative sign. Very important note here, like even if you know the formulas, what are the challenges, the major challenge in solving the problems with the lenses? And that is understanding sign conventions. These formulas will only work correctly if you are using correct sign conventions. If you're not using correct sign conventions, this will yield you wrong results. So remember that there are only 2 points which I'm going to say. First thing, be real. Okay, so because real is positive. So if your object is real, take that as positive. If your image is real, take that as positive. If your image is virtual, your object is virtual, take them as negative. So if we just know this sign convention, we can say reality is positive, right? If things are real, take them as positive. Okay, so distances of di and do will be taken positive or negative. They'll be, if they are, the object is real, do will be positive. If the image is real, di also is positive. So understand like that how to take sign convention of these two things. What about the focal length? So second point is about that. For that, we need to see what kind of lens we are having. So if it is a convex lens, take f as positive. Now tell me where it will be negative. For concave lens. For concave lens, we will take f as negative. So if you remember, these 2 points, our sign conventions are done. But remember, in all the problems, the struggle is only the sign convention. These formulas are easy to remember, but how to apply that, how to use sign convention carefully, that is what the crux of all the problems which we are going to do now. So this is our first numerical. Let's read it. An object is placed 32 centimeter from a convex lens that has a focal length of 8 centimeter. So the focal length is given, and distance of object is also given, 32 centimeter. So they have asked where is the image. The second thing is, if the object is 3 centimeter high, how tall is the image? So they are talking about the magnification here. And what is the orientation of the image? So let's understand by the 2 formulas which we have learned. Let's first of all, let's find out where the image will be. So our formula is, let's try answering that. So first formula, which gives a relation between the focal length and the distance of images and object, is this. So this is what we know. Now it's important to understand our sign convention, how to use it. For that, any question we have, always draw the diagram. Now here is a principal axis. I'm roughly drawing this diagram. Okay, so let's say this is the focus. Okay, symmetrical it is, so both way it will be like this. What is the focal length? 8 centimeters. So if it is 8 centimeter from the optical center, we have to take the distance. Okay, and then at 32 centimeter, 32. So 4 times very far away we are keeping the object. So this is my DO. Okay, this is my DO. Remember, I can say the 8 centimeter this side, and also I can mention it like that because whenever we are talking about the convex lenses, we always assume that they are symmetrical. If not given, it means both way the curvature focuses are same. So this distance from the center to this focus of curvature will also be 8 centimeter. Okay, so what are the sign conventions say? They say if the object is placed here, let me place a object, an arrow here at 32 centimeter. If it is real, take that as positive. So it is a real object, right? It is the light will be, it'll be a source of light. So I can draw light rays from it, and those will be the real lights, right? It's a real light ray. They are not virtual. So this object will be real. So here I can say my DO will be positive. Okay. What about focal length? Focal length also it is a convex lens. According to our convention, we will take them as positive. Yeah. So all the sign conventions I have done here. Now let's find out what is the distance of image. Let's find out DI. So we have to calculate now 1 by F is 1 by 8 is equal to 1 by DI. I need to find it, and 1 by DO is 1 by 32. I will take this fraction, that side, that side. So it will be 1 by 8 minus 1 by 32. Okay, that will be my reciprocal of DI. So here I need to use my calculator. Let me bring my calculator here. So let me use 1 by 8. 1 by 8 minus 1 by 32. Okay, so it is 0.09375. I'm getting 0.09375. Am I done? No, this is just a reciprocal, right? So if I want to find this thing, let me zoom a little there. So if I want to find DI, I need to take reciprocal both sides. So in my calculator, what I will do, whatever the answer, I'm getting 0.09375, I will just reciprocal it 1 by it, and I will get 10.66. So by DI, I'm getting 10.66, or approximately you can say 11 centimeter. Approximately will be the distance of image. So that is my calculate work is done. Let's understand now where the way the image is, and its sign also will give you some answer. So our image is real or not? Image is real. Why? Because see, the sign which is coming of DI is positive. If it comes out to be negative, it has to be a virtual image. So what is happening? The image is forming here. Let's say this is 8 centimeters or somewhere here, and this is the DI we have calculated, which has come as 11 centimeter, approx 10.66. Now we are going, where is the image? Part A is done. So part A, where is the image? Where is the image? So that is 11 centimeter far from the center of, a geometric center or optical center of lens. Let's do the part B, which is asking us the magnification part, like how much the height of the image will be. In part B, they have given us height of the object as 3 centimeter, right? And they're asking then what is the image height? And we know the formula of magnification. So magnification says just do hi by ho. But the problem is we don't know the height of the image, right? That is what we need to calculate. But we know the distances, so it is also equal to minus di by do, right? So we know di we have calculated image distance, and do is already we know 32 centimeter. So it will be magnification will be minus 11 divided by 32. Let me bring my calculator again, and let me calculate this, how much it comes out to be. 11 divided by 32 with a negative sign, so it will be 0.3435. Now I can say 0.345. I'm taking 3 decimal places. If we are getting a fraction, it means the size has been reduced. If it comes out to be 1, it means the magnification is equal 1. It means the same height will be there. But now because it is 3.345, it just means whatever the object size is, if we multiply this fraction, we will get the image size. It will be fraction, it will be smaller. So what is our height of image? That will be just multiplied HO with the magnification. Okay, and remember the negative sign, remember the negative sign. So always remember the signs here, otherwise we will get the wrong interpretation of the answer. So I forgot to, that's why the signs are important here, positive, negative especially. So what is the height of the object? They told that it is 3 centimeter tall. If, then what will be the image size? Let me use my calculator. So I have already calculated this. I will just multiply it by 3, and let's see, one, it is 1.03 or around 1 centimeter tall. Okay, and will I get negative sign? Of course. So negative sign is important. Let me get rid of calculator here. So negative sign is important. It is saying around minus 1 centimeter. I'm getting the height of image. Okay. Now let's read this. This part 1 centimeter is telling what is the size of the image, and this negative sign, this negative sign is telling us that image is inverted. So two information we are getting from here. Now let's go back to our diagram and try to draw how it will be. So if it is a 3 centimeter, this object, so we are getting 1/3 of it. So around, this is 11 centimeters, a little bit like this. So this is the size of, or we can say h of I is 1 centimeter. If this is of 3 centimeter, and this is our, the answer for the part B, and we also have solved for what is the orientation of the image. So we will say the image is inverted. From where we got to know? we got to know when we calculated hi, it came out as negative. The downward thing, if the image is like this, we will take it's positive, and if image is coming like that, we have to take negative. Here's our second question. Let's read it. A 2.25 centimeters tall object is 8.5 centimeter to the left of a convex lens of 5.5 centimeter focal length. Find image position and the height. So what is given? The height of object is given 2.25 centimeter. The distance of object is also given where it is being kept 8.5 centimeter, and focal length is also given 5.5 centimeter. So here's the convention. Both things will be taken as positive. Right? In convex lens, focal length will be taken positive, and object is also real. So we will take these things, positive. Now, what about height of image? This is what they are asking. What is the image distance? This is what they're asking. So we'll use the lens formula. 1 by f will be equal to 1 by di plus 1 by do. And then similarly, if you solve it, you will find out that di is equal to 15.58, or you can say 16 centimeter around. So we'll get di easily from the lens formula. And now further, they're asking about what is the height of the image. So let's calculate that. So we can get it from magnification formula. The distances are known. So minus di by do, and then if you divide it, you will get minus 1.833. So remember here, the factor is not lesser than 1. So it is being magnified. The size has become bigger. The image will be 1.833 times the object. So that is why we will just put if we want to calculate the height of image, we will just put what is the size of the object. We will magnify it or multiply it with the magnification, minus 1.833, and you will get minus 4.125 or minus 4.1 centimeter. So what it tells, this negative sign, it tells that the image is inverted. So that is what we want to know here. Okay, let's read this question. An object near a convex lens produces a 1.8 centimeter tall real image that is 10.4 centimeter from the lens and is inverted. So this information is given to us. If the focal length of the lens is 6.8 centimeter, find distance of object and height of the object. So here also in this question, it'll be important the sign convention which we are using. So let's read and understand this language first. So an object is near a convex lens produces a 1.8 centimeter tall real image. So this is 1.8 centimeter is nothing. We are talking about height of image. Okay, and note here is a real image. Okay, which is at this distance 10.4 centimeter. So distance of image is also given, and 10.4 centimeter it is, okay, from the lens, but it is inverted. So this hi, height of image, I will take negative. So this is an important point here. Okay, and what about the distance? We take distances as positive for real things. So here it's a real image, so it will remain positive. What about focus? For convex lens, the focal length they are given 6.8 centimeter. We will assume it as positive. So this is the sign convention which is important. Actually, this language is all about so that you can reach this conclusion. You can be ready with the solution now. Not a problem. Okay, so now it's just you need to plug these values in the formulas. Let's go step by step. So we know the formula. 1 by f is 1 by di plus 1 by do. Now 1 by f is 6.8, and di this time is given here 10.4 plus 1 by do. Now we are interested in calculating this part, do. So it will be 1 by 6.8 minus 1 by divided by 10.4 is equal to 1 by do. Okay, and now it will be, I need to use my calculator. Use my calculator here. Okay, so it will be 1 divided by 6.8, then I have to subtract 1 divided by 10.4, and don't forget to inverse it so that you can get the value of do. So I will inverse it also. So do will be 19.64, or you can say approximate 20 centimeter. Okay, done. So we got the distance of object where it is. So this part is done. Now, what is the second point? They are also asking about the height of the image. When they are asking about this, we need to go for the magnification. If we are able to calculate what the magnification is, then it is easy stuff as we are doing in the previous questions also. So let me do that. So I'll be finding magnification. So that is minus di divided by do. So minus di is 10.4, and what is do? My do is 20. 20, or I will carry these values and take it as decimal, 19.64. Bring the calculator and calculate this. 10.4 divided by 19.64. That is 0.529, 0 point negative 0.529. This negative sign is important. Yeah. So if we say what we have concluded, that the image size is getting reduced, right, and the image is inverted. That also is given in the question, that image is inverted. Now what we can find, there's another formula. This magnification is also we can calculate by hi divided by ho. And here our importance of sign conventions which we have put here becomes important. So hi I will put as minus 1.8, right, because it is negative inverted, and then ho I have calculated, I need to calculate and that has to be equal to minus 0.529. Okay, so if I need to calculate this, I will take this value here. So minus 1.8 divided by minus 0.529, that will be my height of the object. So let's bring calculator again, and 1.8 divided by 0.529, and it comes out to be 3.4. 3.4. It'll be positive. Why? Because this negative sign will cancel out, right? So that's why our answer will be 3.4 centimeters. So this is the answer which they are asking for. Let's do this question. An object is placed to the left of a convex lens with a 25 focal length so that its image is the same size as the object. So that is the key here. What are the image and object position? So let's try to answer this question. So if you see the key line here is that so that its image is the same size of the object. What does that mean? That magnification is equal to -1. Like being a rough diagram, like this side. So we are getting same size image here. So the size is same. So size is same. That's why the magnification will be -1. So we can say -1 magnification. Let's use the formula minus di divided by do, or we can say minus signs will cancel out. The distance of image is equal to distance of object. So that is what the conclusion is from this line. Now you can apply the formula. 1 by focal length will be equal to 1 by di 1 plus do. But in our case, it is same. Let's say common thing d, and I will say it will be equal to 1 by d plus 1 by d, or 2 by d will be equal to 1 by f. 1 by f, focal length is of 25 so I'm putting that value also. I will take d this side, so and 25 will get multiplied here, so it will be 50. So the distance is 50 This distance is same as the distance of image as well as the object. So here it is 50 to this side, and the image is also at 50 They are equal at equal distances. So that's what for this question. Next question, let's go for that. Calculate the image position and height of a 2 centimeter tall object. So object height is given, HO is given, located 25 centimeter from the convex lens. So DO is 25 centimeter with a focal length of 5 centimeters. F is also given. So I've noted it down here, and they are asking also about the orientation of the image. For that, we need magnification. So first, let's find the image position DI, and we can use this formula. 1 by di plus do. Do we need to take care of any of the sign convention? Let's check. So height of the object, we always keep the object upright, so it will be positive only. Do, object will be 25 centimeter away from the convex, so that will be also positive. It will be real object. It is a source of the light rays, so we can consider that as positive. So this is also positive. Convex lens, we always take the focal length as positive, so all the conventions are correct. And now let me calculate 1 by f is 1 by 5 is equal to 1 by di. That is what I need to calculate. Plus 1 by do, so it will be 25. So 1 by di will be equal to 1 by 5 minus 1 by 25. And let's use calculator here. So calculator 1 divided by 5 minus 1 divided by 25. And let's take an inverse of that so that we can calculate the I, distance of image. So the I is coming as 6.25 centimeter. So that is what, and it is positive, so image is real. Okay, that's done. So let's get rid of calculator for a moment. So this part is done. We got the image position which they are asking in the question. Now let's check, they are asking height also. That's why we need to go for magnification. What we know di, we have calculated, and do already we knew. So let's use the formula minus di divided by do. Remember the negative sign always. And di is 6.25. I need to divide it by do, 25. So let me see, get my calculator again, and it will be 6.25 divided by 25 with negative sign, 0.25. Remember to put the negative sign here. So here we go. What this is the magnification, so the image is getting reduced 1/4 actually. 20.25 is 1/4 of something, so the image size is reduced by 1/4, we can say, or 0.25 fraction, and this means the negative sign means it's getting inverted. So the height of the image will be whatever the height of the object, the magnification factor, and here height of the object is given as 2 centimeter. So we will multiply with magnification minus 0.25. So use the calculator here. It is 2 into 0.25, and we are getting minus 0.5, because this negative sign is there, so I have to take care. Okay, and calculator I'm just multiplying without a negative sign. So minus 0.5 centimeter will be the height of the image. And about the orientation is like how it is kept. So the image is inverted, so we will get the invert image. That's about the orientation about the this object's image.